In question number 31, a thin straight vertical conductor has 10 ampere current flows vertically upward. Let's say at this point current carrying conductor is placed and the current is flowing in upward direction. It is present at a place where horizontal magnetic field is given by 4 into 10 power minus 6 Tesla. We have to arrange the net magnetic field induction at the following points. The first point is at 0.5 meter south of the conductor. Second point is 0.5 meter on the west of the conductor. Third point is 0.5 meter on the east of the conductor. And fourth point is 0.5 meter on the northeast of the conductor. Let's say 4 points are A, B, C and D. As these 3 points are at the same distance from a long infinite length conductor, the magnitude of magnetic field at A, at B and at C will be same. That is mu naught I upon 2 pi r. Mu naught is 4 pi into 10 power minus 7. Current is given 10 ampere divided by 2 pi into r is 0.5, that is 1 by 2. So this will be 4 into 10 power minus 6 Tesla. Here we can see that the magnitude of magnetic field at point A, B and C and the horizontal component of magnetic field are same. Now magnetic field at point D can be given by PD is equals to under root. The magnetic field due to this conductor is same as the horizontal component of Earth, so is equals to B square plus B square plus 2AB, that is 2B into B cos this is 45 degree and this angle is 90, so total 135 degree. Simplifying this, we'll get BD is equals to under root 0.59B. Now checking the direction of magnetic field at different points. Here the current is in upward direction, so the magnetic field will be in this way. At point C the magnetic field is in upward direction, in north direction, and the horizontal component of magnetic field is in downward direction. So net magnetic field at point C will be B minus B, that is 0. Now the magnetic field at B due to the current carrying conductor is in the downward direction, and magnetic field due to Earth is also in downward direction. So magnetic field at B is equals to B plus B, that is 2B. Now magnetic field at point A. Here due to conductor the magnetic field at point A will be towards east, so this is magnetic field B. The resultant of this 2 will be root 2B. So magnetic field at point A is root 2B. If we arrange these points in ascending order, the order will be B, A, D, C. At C magnetic field will be minimum. So option 4 is correct option. In question number 32, a straight section PQ of a circuit lies along x-axis at x is equals to minus A2 to x is equals to plus A2 and carries the steady current I. We want to find the magnetic field due to this conductor at point x is equals to A. As this point is on the line of conductor, the magnetic field at this point will be 0. So option 4 is correct option. In question number 33, we want to find the magnetic field at the center of circular loop of radius r. Here there are two elements, one is circular loop and another is infinite long straight conductor. The magnetic field due to circular loop at the center will be inside the page, and due to the long conductor will be outside the page. So to find net magnetic field at the center, the fields are subtracted. Let's say magnetic field due to circular coil is B1 and magnetic field due to conductor is B2. B1 will be mu naught I upon 2R and B2 will be mu naught I upon 2 pi R. So net magnetic field will be B1 minus B2, that is mu naught I upon 2R minus mu naught I upon 2 pi R. So B is equals to mu naught I upon 2R into 1 minus 1 upon pi. So B will be mu naught I upon 2 pi R into pi minus 1. So option 2 is correct option. In question number 34, we want to find the net magnetic field at center O. Here there are three elements, straight conductor AB, the arc BCD and the semi-infinite long wire DE. Here magnetic field due to AB will be 0 as point O is lying on the line of AB. Now magnetic field due to arc BCD will be outside the page, and due to this semi-infinite long wire DE will also be outside the page. So for net magnetic field we will add both the magnetic fields. Let's say magnetic field due to this is B1 and due to the semi-infinite wire is B2. So B naught is given by B1 plus B2. B1 is due to whole circle, magnetic field at center is given by mu naught I upon 2R. So due to half circle, it will be half of mu naught I upon 2R plus the magnetic field due to semi-infinite wire is half of mu naught I upon 2 pi R. So total magnetic field will be mu naught I upon 4R plus mu naught I upon 4 pi R. So option 3 is correct option. In question number 35, it is given that magnetic induction at the center due to motion of an electron in first Bohr orbit is B. Let's say radius of first Bohr orbit is R1. We want to find the magnetic field due to the motion of electron in second Bohr orbit. Let's say radius of second Bohr orbit is R2. Here we know that magnetic field at the center will be mu naught I upon 2R. So we can write B is inversely proportional to radius. And we know that radius is directly proportional to n power 5, where n is the number of Bohr orbit. So we can directly write B is inversely proportional to 1 divided by n power 5. So B2 by B1 is equals to R1 by R2 is equals to N1 by N2 whole power 5. Here B2 by B is equals to N1 is 1 and N2 is 2 whole power 5. So B2 is equals to B divided by 2 power 5, that is 32. So option 2 is correct option. In question number 36, the magnetic field induction at the center of circular coil of radius 5 cm and carrying a current of 0.9 ampere is given by mu naught I upon 2r. But here all the options are in the form of epsilon naught. The speed of light in vacuum is given by 1 upon under root mu naught epsilon naught. So mu naught is equals to 1 upon c square epsilon naught. Replace this value. So B is equals to 1 upon c square epsilon naught into 2r, that is 10 by 100, into I. I is given by 0.9 ampere. So B is equals to 9 divided by the speed of light in vacuum is 3 into 10 power 8 meter per second. So C square will be 9 into 10 power 16 into epsilon naught. So magnetic field will be 1 upon epsilon naught into 10 power 16. So option 1 is correct option. In question number 37, we want to find the magnetic field at the center of an equilateral triangle of side 2r and carrying the current I. Here, the triangle can be considered as the combination of 3 finite length wires. We will find the magnetic field due to one wire and then multiplied with 3, because the magnetic field due to all 3 conductors at the center O is in the same direction, so their magnetic fields will be simply added. Let's say we want to find the magnetic field of wire AB at point O. This point, this length for an equilateral triangle is L by root 3. So magnetic field due to AB will be mu naught I divided by 4 pi into L by root 3 into sine of this angle is 30 degree, this angle is 90, so this angle will be 60 degree. Sine 60 degree plus sine 60 degree. So B1 will be root 3 mu naught I upon 4 pi L into 2 times sine 60, that is root 3 by 2. So B1 will be 3 mu naught I upon 4 pi L. So B net will be 3 times B1, that will be 9 mu naught I upon 4 pi L. So option 1 is correct option. In question number 38, same current I is flowing in 3 infinitely long wire along positive X, positive Y and positive Z directions. The magnetic field at the point 0, 0, minus E, that is we want to find. Here the positive Z axis is in upward direction and negative Z axis is in downward direction, that is downward the page. The magnetic field due to current carrying conductor placed along positive x-axis will be in the positive y direction, and magnetic field due to the conductor along y-axis will be along the negative x direction. The magnitude of magnetic field will be same, so B net can be given as mu naught I upon 2 pi E j cap minus mu naught I upon 2 pi E I cap. So option 1 is correct option. In question number 39, 2 square loops are placed concentric of side length capital L and small l, having current capital L and small I respectively from them. their centers are coinciding, we want to find the magnitude of the torque on the smaller loop. Here, the torque on the smaller loop can be given as N I E V sine theta. N will be 1. Here, theta is the angle between the magnetic field and the area vector. The magnetic field linked with the smaller coil is the field of the larger coil. The magnetic field of the larger coil will be perpendicular to this plane, and the area vector of the smaller coil is also perpendicular to the plane. So angle between A and B will be 0. So torque acting will also be 0. So option 4 is correct option. In question number 40, a coil in the shape of an equilateral triangle of side L is placed between the pole pieces of a permanent magnet, let's say north and south, such that the magnetic field B is in the plane of the coil. Due to current I in the triangle, torque tau is acting on the triangle. We want to find the length of the triangle. Torque acting is given by N I A B sine theta. Number of coil is 1. So I area will be root 3 by 4 L square. The area of equilateral triangle is root 3 by 4 L square into B. Theta will be 90 degree, as this is magnetic field, and the area vector will be perpendicular to the magnetic field. So L square is given by 4 tau divided by root 3 I B. So L will be 2 tau divided by root 3 I B whole power 1 by 2. So option 3 is correct option. In question number 41, two long straight conductors with current I1 and I2 are along X and Y axis. We want to find the equation of locus of points of zero magnetic induction. Here, to have zero magnetic induction, the magnetic field due to these two conductors should have same magnitude and opposite directions. If I think about direction, in the first quadrant, the magnetic field due to the I1 current is in outward direction, and magnetic field due to I2 current is in downward direction. So there is possibility of zero induction in first quadrant as well as in the third quadrant. So the locus will be a straight line. Let's say this distance is y and this distance is x. At this point, magnetic field due to I1 is given by mu naught I1 divided by 2 pi y, as y is the perpendicular distance. And at this point, the magnetic field due to I2 is given by mu naught I2 divided by 2 pi x. Here the magnitude of both the magnetic field should be same. So we can write y is equals to I1 by I2 into x. So option 3 is correct option. In question number 42, the ends of a circular coil of radius r and number of turns n is connected to the two terminals of a cell, and the magnetic field at the center is B. Now the number of turns are made 2n, keeping the radius constant. We want to find the new magnetic induction. B is given by n times mu naught I upon 2r. Here radius is constant, so we can write B is directly proportional to n. So B dash yb is equals to 2n yn. So B dash is equals to 2b. Option 2 is correct option. In question number 43, we want to find the magnetic dipole moment of the loop. The magnetic induction at the center of that circular coil is V and area of the coil is A. The magnetic dipole moment is given by I into A. The magnetic field can be written as mu naught I upon 2R. So I can be written as 2RB divided by mu naught. Area is given by pi r square. So radius can be given by under root A by pi. So I will be 2 by mu naught under root A by pi into B. Magnetic moment will be I into A. So M will be 2BA root A divided by mu naught into root pi. So option 4 is correct option. In question number 44, a long straight conductor carrying current I is lying along y-axis. Charge Q is projected with velocity u j cap from point 0 A. There are two observers, one is at rest and one is moving with constant velocity. We want to find the force experienced. Force experienced is given by QVB sine theta. Here V is U. Magnetic field will be due to this conductor and it will be perpendicular to the velocity. So theta will be 90 degree and magnetic field is given by mu naught I upon 2A. Now no observer is accelerating, so this force will be common to both the observers. So option 4 is correct option. In question number 45, in a certain region of width A, the magnetic field exists. A charge is projected with velocity v in this magnetic field. There are different options for the maximum angle of deviation. The conditions are if r is less than a, then it will complete the circle and come out of it. So in this case, the deviation will be 180 degree. If r is equals to a, then in this case, if particle starts from here, it will move like this and it will come outward in this direction. So in that case, these two distances should be same. So when r is equals to a, the deviation will be pi by 2. So option 4 is correct option. In question number